Hello, satellite designers. I'm Nick, and I want to spend the next few minutes talking to you about the major design of our Cape 4 satellite. I want to remind you guys that we're in our third year with this thing, and we still haven't frozen our block design green. So I want to start off by looking at what Oregon State is doing. Look here. They got a main processor board, and all their subsystems are via by CAN bus. That's a good indication that they got it right. We independently arrived at them, so maybe we're right too. So let's get started. So the CDH design objectives. Well, first of all, we talked about this, but let me just restate it one more time. We want to follow the KISS principle. We got to get this sucker built. We want fully redundant two processors. If one fails, we want the other to pick up and go on, and we don't want to make a brick up there. Our comms will have two LoRa radios, both controlled from either process. We want over-the-air software updates. We want to make it adaptive data rate, which means when the link margin improves, we want to increase the data rate. And we want to have some non-volatile storage on both of our processors. And of course, the comms over here, the VHF radio has two power settings. One is 20 dBm and the other is 37.5 dBm. And the UHF radio has a whopping 20 milliwatts, or 20 dBm. Now, let's get into block diagram. So the overall big picture is we got about 8 of these processors sitting in the back plane, and we got our CDH board. Our most controversial board to date is this guy, right? So let's talk a little bit about them and isolate it. So here it is. Let's start off with the radios. We've got a VHF and a UHF radio, and of course, we said we had two power settings out of our VHF radio. So here's our amplifier, and here's a bypass switch. So this thing will draw about 10 watts, and we won't turn this thing on very long or very often. We've got, of course, power detectors and our antennas, and so we got a VA and a U antenna, and here are our radios. Now here's the change, is that these radios communicate to the processor via SPI bus, and we have switches, SPI switches, so that this radio can either talk on this one or it can talk on this one. And if we're cute enough, maybe we can make them talk at the same time. I'm not sure we want to do that. So we picked STMs. We haven't quite determined which flavor we want. And undesigned as there is a boot controller. Is that when we power up, we want to be able to boot on either one of these things. And if we get a failure, we want to be able to automatically switch. And we want this in hardware. You know, damn high energy particles flying around and want to kill something. So we want to try and do this in hardware. And of course, we're going to talk to them via CAN bus. Now look, this is pretty simple, straightforward. Nothing fancy in here. Doesn't need to be. All right? Need to work. All right, so now let's talk a little bit about the philosophy. We haven't done a lot of philosophy about software design, but here's my idea. First of all, we're going to have 3 interrupts, maybe more. And of course, we definitely need to be able to update our watchdog timer. All right, and so I think we can do this on a timer interrupt, and about every 100 milliseconds, we want to say go wag our watchdog timer. And of course, we have our radios, and what's important here on our radios is that when we receive ground communications, these things generate an interrupt, and on the interrupt, the first thing we do is we go grab about 255 bytes out of that buffer on that radio and stick it in the memory. And then we're going to set a flag over here saying we got go look at it. So either radio can generate an interrupt. Now let's get started with the main loop. Now this is a little controversial, but let's think about this. So the first thing is when we power up, we got to initialize a bunch of stuff. So we go initialize all our sensors, whatever we got to do. And then we get into this, what I call a round robin deal, right? So the first thing we do is we go over here and we say, power board, you still alive? Do you have any information? You got any health checks you want to send to me? No. Then we go to attitude. Attitude, you still alive? Yeah, I'm still alive. You need anything? You need any controls? We got anything to tell you? No. And we go around to all our subsystems, right? And we just poll them. 1, 2, 3, 4, we just poll them. All right. And in the main loop, we're going to say, we're going to check and see if we've got a COM flag going. So it says, look, this thing says, I want you to do something. We set this flag, we go parse this command. Maybe it's a ping command. Maybe it's a give me a help thing. But anyway, this thing goes over here and then we check our schedule in the RAN loop. If we got to schedule something, we schedule it, we do it, we keep going, right? Now we got to set some rules about how long we can stay out of this loop, you know, if we're going to do a file transfer. You know, and it may extend several minutes. We cannot check this loop without that. So when we do long jobs, we got to make sure that we interrupt and get around this loop once in a while. The alternative is to go to a real-time operating system, which none of us, other than Michael, has a lot of experience. None of us has a lot of experience, and not only Michael is probably the only one in here who really dealt with that. And at this late stage of the game, 3 years out, it's time for us to quit fooling things and get things working. All right, guys. My challenge is that no question about it, these are my ideas. And I don't make all the decisions right. And if you see something that bothers you, you got to speak up and improve this design. Now, I know some of you guys already think I'm suffering from accelerated Alzheimer's, but doggone it, this is your project. I'm here to help you facilitate it. So if you don't speak up, shame on us. That's good. So let's go get this thing built before NASA gives up on us, or the Lord gives up on me. Boost me into higher order. That's all I got. Hear from